So, that's in the physical seat of food. That is the source of our emotions or decision making or passions or pains and everything else. Well, it's the brain, and it's said to be the most complex mechanism in the known universe. You might expect, given all it is and given all it does, that will look very pretty. Philips shimmering lights and glass tubes and mysterious colors. But in fact, it looks really kind of gross. It looks the 3-day old meatloaf. It's grey when you take it out of the head, and inside the head it's bright and red because of all the blood. In fact, it turns out very surprisingly that the source of our mental life, of our consciousness, is met. In fact, you could eat have eat people have eaten brains. I've had brain with cream sauce. Not human brain, mind you, but I've had brain with cream sauce. It's not bad, but it makes the puzzle all the more harder. How can this fleshy thing give rise to mental life? That's the question I want to explore in this lecture and the rest of the lectures. I want to do so by starting with the smallest relevant parts, different parts of neurons. Then explore how the neurons are connected together, how they are wired up, how we form different subparts of the brain, like the hypothalamus and the frontal lobe. Finally, talking about the brain and the larger perspective, looking at the two halves of the brain, the left half and right half, and how they interact. Now, there's a lot of stuff in the brain, a lot of chemical stuff, a lot of different parts, but there the action is the part that does the thinking. The part that is the focus of most of our research is the neurons. It's not an accident they call the study of the biological basis of food neuroscience, because it all comes from the neurons. So you can see here a picture of neurons interacting together. Here's a diagram that depicts a typical neuron. So that you see is the dendrites, and dendrites receive signals from our neurons, either excitatory like pluses or inhibitory minuses. When they get to be the cell body which sums up these pluses and minuses. When you reach a central threshold, a certain amount of pluses, there's neural firing. Firing takes place through the axon, and the axon is much longer than the dendrites. In fact, for some motor neurons, it's very long indeed. There's axons running from your spinal cord all the way to your big toe. You could think of it of the relative size of things in terms of a basketball and a 40-mile garden hose. Surrounding the axon is, let's call it, a myelin shelf. The myelin shelf is, you can think of it as insulation, as fatty tissue like insulation on a wire. So the information comes through the dendrites and summed up in the cell body, and it's transmitted through the axon. So that's neurons do, is they sum up the transmit information, and we know that there's a lot of them. By some estimates it's 100 billion. All the estimates tend to be very different and very rough, but there's billions upon billions of neurons, and each connects to thousands, maybe tens of thousands of other neurons. So the fact that you have something of this degree of complexity, this degree of structure which there's no way to replicate in any machine. The number are just too big is why people might describe the brain as the most complicated machine in the universe. At least this is fitting. It's made of matte maybe, which is kind of disappointing, but at least it shows its incredible internal structure. So neurons come in three flavors. There are sensory neurons, which take in information from the environment, from the external world. There's motor neurons, which go from the brain out to your motor control. So, if you touch something hot and you feel the pain, that's sensory neurons. If you rent your hand back or you reach for something, that's motor neurons. Finally, these interneurons, which connect different neurons without making contact with external world. Either through sensation or thought motor action. Now the main thing to think about for neurons and neuron feeling is that it's all or nothing. It's like firing a gun or sneezing. Neurons either fire or they don't. Now you might think that's a little bit strange, particularly when you think about sensory neurons, because your experience seems to be a continuum. So you have sensory neurons in your eyes, and you can distinguish from a very dim light and a very bright light. You have sensory neurons in your fingers, and you could distinguish between gently touching something versus being tapped on the tip of your finger or something. But still, the neurons are all or nothing. The way they get to this continuity of experience is that neurons can code for intensity in different ways. So, one way is in terms of the number of neurons that fire. If X neurons corresponds to a mild experience, X times 10 neurons may correspond to an intense experience. Another factor is the impulse frequency of individual neurons. An individual neuron might denote a mild sensation by doing fire, 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 fire. Well, it might denote an intense situation with fire, 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 fire. So, you have neurons, and the neurons talk to each other. They talk to each other because axons, an axon of the neuron will communicate with the dendrites of another neuron. A long time ago, people used to think that neurons were wired up together like a computer. But in fact, neurons don't actually touch one another. There is a gap between the axon terminal of one neuron and the dendrite of another one. A very tiny gap, typically of like 110,000th of a meter wide. This gap is known as a synapse. Then the one neuron fires, the axon releases neurotransmitters. There are chemicals that shoot out over that gap and affect dendrites and other neurons. As I said before, the effect of these neurotransmitters could be excitatory, which is that they raise the energy, so they increase the likelihood of a neuron feeling, or inhibitory, so that they bring down the likelihood of a neuron feeling. That's interesting is that different neurons shoot out different neurotransmitters, so they have different effects on other neurons that they made contact with. In fact, a lot of psychopharmacology both attempts to cure various psychological and physical diseases by giving medicine or recreational psychopharmacology designed to increase pleasure of different forms. It sometimes helps people walk or help people focus. Works by feeding with the neurotransmitters, and this can be either antagonists. They lower down intensity of things by binding to the dendrites, making it hard to create more neurotransmitters, or they can increase the amount of neurotransmitters available in different way agonists. So you are either pumping up the volume or turning down the volume. So we're thinking about different drugs and their effects. There's curare. Curare is a drug that's used by South American Indians. It's an antagonist. It blocks motor neurons from affecting their muscle fibers. It keeps your motor neurons from working, and that it does, it's paralyzed you. And in large enough doses, it kills you because motor neurons also keep your heart beating. So shut them down and you die. There's alcohol. Now alcohol also has an inhibitory effect. You might think that's strange because when I drink alcohol I get all excited and happy and goofy. But you have to keep this in mind here. The way alcohol works is it inhibits part of your brain that does the inhibition. So you have part of your brain that says, don't say that to another person, keep your pants on, stop yelling, and alcohol basically inhibited that part of the brain, making you more exuberant. When all the course of things in the course of drinking too much, it also inhibited other parts of the brain. So you could pass out and fall on the floor, and in large enough doses, die. So both curare and alcohol in different ways bring things down. Other drugs bring things up. So amphetamines, for instance, increase the amount of norepinephrine, which is another neurotransmitter that's responsible for genetic general arousal. And this is how drugs like speed or cocaine work. Other drugs like Prozac or L-Dopa influence neurotransmitters in ways that they increase. For instance, the supply of dopamine or serotonin, which can be relevant for issues like Parkinson's, which seems to be related to too little dopamine, and depressions, which is related to too little serotonin. So these drugs work by influencing neurotransmitters, either by directly pumping in more neurotransmitters or increasing their supply in different ways, or stopping them from having effects by binding them or sucking them up in different ways. But they work through their effects on neurotransmitters. So the more general idea is the way neurons lead to thinking is that they form clusters or networks. These clusters and networks are computational devices that do interesting things like recognizes face, or walking upright, or understanding sentences, or doing math, or experience great sadness, or falling in love, and so on. We know that's possible because we create computing machines that work in certain ways. That's if you wire up a computer machine in certain complicated ways. It can do mathematics, play chess, do fine simulation, and so on. So you may be interested in the project of computational neuroscience, which tries to ask the question, how are neurons wired up to do interesting things, and uses our own success at computational theory as a model. Then sometimes takes the inference the other way around, which is you can see how people do it and then use this knowledge of how people do it to create computational systems that can do it as well. So how is the brain wired up? Well, you might imagine that's wired up like a portable computer, like a laptop, like the sort of computer you are looking at now. Into some regards it is. But there's a couple of reasons why it can be, and both of them have to do with how well the brain works. So, first, the brain is highly resistant to damage. If you get a knife to the brain, if you get damage to the brain, it won't typically shut down the whole system. The information and capacitors somehow distributed across neurons in such a way that makes them extremely resilient to damage. While in contrast, somebody could open up the back of your laptop, pull out a chip, and the whole thing is ruined. The whole thing will stop working, but the brain is wired up in a certain way that makes it highly resilient. The second thing is the brain is wired up in such a way that makes it work very fast. So computers can do millions of operations per second because they are purely electrical, but brain tissue is much slower and can spend their time to do many steps. So, to put it a different way, if your brain was wired up like a computer, it would be so slow as to be inherently unusable. It has to be wired up in a way that's more efficient, that allows for the slowness of brain tissue and neurotransmitters, and can still compute things at a human level, which is often blindly fast. Because of this, there has been a huge interest in massively parallel systems and complicated neural networks which are wired up as we believe the brain does, and as such, we are helping computers to do things based on our understanding of the brain that they could never do before. The details of this is something they are going to talk about through the course. They're not actually going to end up explaining different capacities directly in terms of neurons, because we can't and because we want it to have high-end level explanation. So when I talk about how people learn language or how do they recognize faces, we're not going to talk much about neurons in particular, but we talk about different brain areas and how they work.